Here is the existence and uniqueness theorem for initial value problem of first order ODEs. Let R be a rectangle containing the initial point x0, y0 in the domain D. F, a function on two variables x and y, be continuous at all points x, y in the rectangle R, where R is defined as x minus x0 less than a and y minus y0 less than b. And our function f is given to be bounded on the rectangle R. That is, the modulus of f x, y is less than some constant k for all xy belonging to R. Here, the rectangle R is basically a rectangle which contains the point x0, y0, and it is given here that x0 minus x is modulus is less than a and modulus of y minus y0 at less than b. So our function f satisfies these two conditions, that it is continuous and it is bounded on the rectangle R. Then the theorem states that the initial value problem of the first order ODE, namely y dash is equal to f of x, y with the initial condition, namely y of x0 is equal to y0, has at least one solution yx defined for all x in the interval modulus of x minus x0 less than alpha, where alpha is given by minimum of a and b by k. So what it states, that the initial value problem of first order ODE, namely y dash is equal to f x, y with this initial condition, will definitely have one solution. So it gives the existence of the solution. On which domain? On the interval where modulus of x minus x0 is less than alpha. And how to determine the alpha? In this case, the alpha is the minimum of a, that a coming from here, and b by k. So the b coming from here and k is coming from this bound. So this gives us the alpha. So this gives us the existence of the solution. Now next condition will state how do you get the uniqueness of the solution. So for uniqueness of solution, we need to assume in addition to the above condition that f satisfies Lipschitz condition with respect to variable y in R. That is, this condition is satisfied. Modulus of f of x, y1 minus f of x, y2 is less than m times modulus of y1 minus y2 for all x, y1 and x, y2 in the rectangle R. So if the Lipschitz condition is also satisfied in addition to the above conditions, namely continuity and boundedness, then we have uniqueness of solution. That is, the solution yx defined at least for all points x in the interval x minus x0 less than alpha, where alpha is obtained from the above formula, is unique. So this gives the uniqueness of the solution. What is unique here? The solution that is obtained here not only exists but is also the unique solution. There does not exist any other solution of the initial value problem. This is the existence and uniqueness theorem for first order ODE. So we'll see some examples of functions which satisfies Lipschitz condition from our definition and our other results that we obtained in the previous slide. Look at this function. Fx is defined to be equal to sin x. The question is whether this function fx is equal to sin x is Lipschitz continuous over R, that is over the entire real line. How do you check this? You can pause the video and try to solve yourself. Note that a function is said to be Lipschitz continuous if it satisfies Lipschitz condition. The answer to this question is that the function fx is equal to sin x is Lipschitz continuous. This can be verified using mean value theorem. The second question is the function fx is equal to x square globally Lipschitz continuous over R? By globally Lipschitz continuous, we mean that in the definition of Lipschitz condition, the x1 and x2 can be any two real number. Please pause the video and try to answer this question. The answer to this question is no. The function fx is equal to x square is not globally Lipschitz continuous. The reason behind it is when you calculate the modulus of the quotient, where in the numerator we have f of x1 minus f of x2, and in the denominator we have x1 minus x2. This quantity is equal to modulus of x1 plus x2. Now we can choose x1 and x2 to be very large numbers, and so this quotient cannot be bounded by any constant. So this is not Lipschitz continuous globally. However, it is Lipschitz continuous over a closed interval of R. We have seen that this function is Lipschitz continuous over any closed interval in our previous slide. Such a function is called locally Lipschitz continuous. So it is not globally Lipschitz continuous, but it is Lipschitz continuous over an interval. So such a function is called locally Lipschitz continuous over R. The third question is the function fx is equal to 1 by x square globally Lipschitz continuous on the interval, closed interval from alpha to infinity for any alpha greater than 0? You can pause the video and try to answer this question. The answer is yes. This function is globally Lipschitz continuous, and here again the solution follows using mean value theorem. We will see some examples. The first example is y dash is equal to y raised to 1 by 3. So if we say y dash is equal to f of x comma y, then f of x comma y is equal to y raised to 1 by 3. It turns out that in this example, fx comma y, which is equal to y raised to 1 by 3, does not satisfy Lipschitz condition. So it does not satisfy the uniqueness condition. And it turns out that in this example, there are more than one solution. The solution is not unique for this initial value problem. Here the initial condition is y0 is equal to 0 in the rectangle R, where modulus of x is less than or equal to a, modulus of y is less than or equal to b. So here the function f x comma y is continuous in R, and hence existence is guaranteed of the solution of this differential equation. Y dash is equal to y raised to 1 by 3, y equal to 0 everywhere is a solution, and it also satisfies the initial condition. So we can say, in other words, that the explicit solution y is equal to phi 1x, where phi 1x is equal to 0, that is the solution of this differential equation. Also, you can check that the explicit solution y is equal to phi 2x, where phi 2x is equal to 2 by 3x bracket raised to 3 by 2 if x is greater than or equal to 0, and 0 if x is less than or equal to 0. This is also a solution. y is equal to phi 2x is also an explicit solution of this differential equation. So what we have done is, if we solve this differential equation, one of the solution you get is y is 0 everywhere. Other solution is y is equal to 2 by 3x bracket 4 raised to 3 by 2. But you can patch up this solution to get more than one solution, which will still satisfy the initial condition y 0 equal to 0. This solution is obtained by patching up the two solutions. And this function is differentiable, and so both the explicit solutions are solutions of this differential equation. So this should imply that it does not satisfy Lipschitz condition, and we can verify that. So we compute the modulus of f of x comma y1 minus f of x comma y2 divided by modulus of y1 minus y2, and this quantity is equal to y1 raised to 1 by 3 minus y2 raised to 1 by 3 divided by modulus of y1 minus y2. So here, if we choose y1 to be equal to delta and y2 to be equal to minus delta, then what you get here is 2 times delta raised to 1 by 3 divided by 2 times delta, which is 1 by delta raised to 2 by 3. And so this quantity 1 by delta raised to 2 by 3 is unbounded when you choose smaller values of delta, because as the delta is smaller, 1 by delta raised to 2 by 3 is very large. So there is no bound for this quotient, and hence Lipschitz condition is not satisfied. And it has two solutions, because the conditions of uniqueness of solution in the existence of uniqueness theorem is not satisfied. So the solution exists, but it's not unique. The next example is y dash is equal to y square. So if we say y dash is equal to fx comma y, then fx comma y is equal to y square. So fx comma y is equal to y square is a continuous function, and it is also Lipschitz continuous with respect to the second variable y. So it satisfies the existence and uniqueness theorem conditions. So in this case, we will find out the alpha in the existence uniqueness theorem. Here we had this alpha, which gives us the interval x minus x naught modulus less than alpha. It gives us the interval on which the solution exists and is unique. So we find out alpha in this example. The initial condition is y of 1 is equal to minus 1. Find the alpha in the existence and uniqueness theorem. So here we consider the rectangle which is drawn in this figure. So rectangle is R, which is modulus of x minus 1 less than a, modulus of y plus 1 is less than p. So the rectangle will look like this, which contains the point 1 comma minus 1, which is the point determined by the initial value condition. Now fx comma y here is y square. So the fy, that is the del f by del y, is equal to 2y. Both are continuous on a closed rectangle. So since it is continuous on a closed rectangle, fy is equal to 2y, so it is also bounded. So it has bounded partial derivative with respect to the second variable. So it satisfies the conditions of existence in uniqueness theorem of initial value problem of first order ODE. Now, in order to determine alpha, recall what all we need to know. So, in order to determine alpha, we need to know what is A, what is B, and what is K. So, K here is a bound for our modulus of f of x comma y. So, we want to find the best possible alpha in our case, the maximum value for alpha, so that we get a large enough interval. So, in order to determine the k, we already know the a and b that is given here. I want to determine the k for our problem, namely the one which bounds our modulus of f of x comma y. So, modulus of f of x comma y is equal to modulus of y square, which is less than modulus of minus b minus 1 modulus square. This you can clearly see because here the value of y is such that y plus 1 modulus is less than b. So you can see in which range y lies. From that you can easily determine that modulus of y will be less than this particular quantity. And the square of this modulus is equal to the bracket b plus 1 bracket close whole square. So this quantity bounds our modulus of f of x comma y. So by our formula, we get alpha to be equal to minimum of a comma b by b plus 1 square, as was the previous slide. So this m was the k that appeared in the denominator is now replaced by b plus 1 square. So we want to determine here the best possible alpha, the biggest alpha for our example. For that, we have to simplify further the number here, b by b plus 1 square will determine the maximum value of this function on the variable b. So consider that fp is equal to b by b plus 1 whole square. So this quantity we want to find the maximum value. So we know how to find the maximum value. We take the derivative of this. So derivative of this is b plus 1 cube in the denominator and in the numerator 1 minus b. So from this you see that f dash b is equal to 0 when b is equal to 1. At the point b is equal to 1, f has maximum value because f dash is positive for b less than 1 and f dash is negative for b greater than 1. And at 1, f takes the value 1 by 4. Now we will check what happens when a is greater than 1 by 4. So we know that the function fp, which is equal to b by b plus 1 whole square, is less than 1 by 4. So that quantity is less than a in this case for all b greater than 0. So alpha, which is minimum of a and b by b plus 1 whole square, that is fp. So alpha is equal to actually fp, because fp is smaller than a, so the minimum will be fp, and fp is b by b plus 1 square, which is less than 1 by 4. So in this case, alpha is anyway less than 1 by 4. If we take the case where A is less than 1 by 4, then obviously this alpha is going to be less than 1 by 4, because both the quantities A and FP are less than 1 by 4 in this case, and thus in any case we have the alpha to be less than or equal to 1 by 4. So the best hope is that alpha is equal to 1 by 4 for getting the maximum interval, the biggest possible interval around the initial value point. So this alpha can be achieved when you choose b equal to 1 and a greater than or equal to 1 by 4, or even if we choose a to be equal to 1 by 4, then we will have alpha to be equal to minimum of a and 1 by 4, because our fb function takes the value 1 by 4 at the point 1. So it is minimum of a and 1 by 4, and if a is greater than or equal to 1 by 4, then the minimum of this is 1 by 4. So this is how we can obtain the best possible value of alpha, that is the biggest interval around our initial point. So the initial value condition is y at 1 is equal to minus 1. So we are looking at the point 1 and an interval around 1 of radius 1 by 4. So what do we mean by that? We mean that we are talking about the interval 3 by 4 to 5 by 4. X varying between 3 by 4 to 5 by 4. We have the best possible value of alpha, that is 1 by 4. The theorem which gives that the initial value problem has the unique solution in the interval, the biggest possible interval, namely modulus of x minus 1 is less than 1 by 4, which means that x varies between 3 by 4 and 5 by 4. So this is the result we obtain, the best possible interval we obtain from the formula existence uniqueness theorem. But the biggest possible interval that is given by the existence uniqueness theorem may not be the biggest possible interval for individual problems. In general, when we don't know much about the nature of the initial value problem, we can obtain the best possible interval. But in certain particular differential equation, we can actually show that solution exists for a much larger interval. The theorem guarantees that existence uniqueness theorem only in a small interval. The theorem does not give the largest interval, but the solution is unique. So if you take this particular problem, so the problem was y dash is equal to y square with the initial condition y1 is equal to minus 1. Take this particular problem and solve it by separation of variable. What do you get? You get dy by y square is equal to dx. So when you solve it, the solution that we get is minus 1 is equal to xy. So xy is equal to minus 1 is the solution. If we solve that differential equation using separation of variables and then apply the initial condition. Can you think of extending the solution to a larger interval? Is it valid for a larger interval? The answer is yes. If you plot this solution in the xy plane, it looks like this red curve, where the initial point only 1 comma minus 1 is plotted here on the curve. So you can see the solution exists and is unique on the interval where x varies from 0 to infinity. So it is not just 3 by 4 to 5 by 4 as was determined by our theorem, 3 by 4 to 5 by 4, but rather it is much bigger. It is from 0 to infinity that we have a unique solution. So It the existing uniqueness theorem does not give the largest interval for individual problems, but it is useful in general to get the largest possible interval for any given differential equation. The same formula can work.